Hello, I am Professor Nakage from University of Manitoba, Canada, and this module is on power system dynamics. I have divided this module into 4 lectures. In the first lecture, I am going to review the synchronous machine models. In the second lecture, I will introduce small signal model of one machine connected to an infinite bus system and how to design a power system stabilizer for that system. Third lecture is going to be very brief. I will introduce how to develop the multi-machine power system model, and then finally I will talk about state space analysis and the design of a power system stabilizer for a multi-machine power system. I will give a brief revision of modeling of synchronous machines. I am not going to derive any equations in the lecture. The derivation of these equations will be left for the students as tutorial exercises. I will explain the equations in a qualitative manner only. For more details, please refer to Power System Stability and Control by Prabha Kundu. In this diagram, we see the representation of an electrical machine as a set of coupled coils. On the right, we have the stator coils A, B and C. Voltage induced across these coils are EA, EB and EC. Currents in the coils IA, IB and IC are leaving out of the coils. On the left, we have the rotor coils. FD is the field winding with an induced voltage of EFD and a current IFD going into it. The magnetic axis of field winding is called the D axis. The damper windings or amortisseur windings are shown as short-circuited coils on each axis. If there is only one damper winding on the D axis, we use the notation 1D. If there are two damper windings, we use the notation 1D and 2D. The same applies to the quadrature axis windings. The axis of phase A is the direction of magnetic flux produced by a current in coil A. Now we can write voltage equations. The voltage induced in any coil is equal to the rate of change of flux in that coil minus the voltage drop due to the internal resistance of the coil. We can write this equation for phase A, phase B and phase C. The magnetic flux in any one of the coils is made up of self and mutual components. For example, in equation 4, we have flux in coil A. The first term is the flux due to its own current IA, and LAA is the self-inductance of coil A. The second term in the flux equation is the flux induced in coil A due to the current in coil B, and LAB is the mutual inductance. Some of these inductances depend on the relative position of the rotor. Some are independent of the position of the rotor. I am going to let the students figure out how these inductances vary with the position of the rotor. I will simply present these relationships. These equations describe how the stator self-inductances vary with the relative position theta of the rotor. These equations show the dependency of stator to stator mutual inductances on the rotor position theta. Similarly, mutual inductances between the stator winding and the rotor winding change with theta. And finally, the self and mutual inductances of the rotor windings do not depend on theta. Now let us focus our attention to the voltage and flux equations that we presented in slides 2 and 3. So let's go back to slide number 3. It is clear that the analysis of the behavior of a machine becomes very complicated because we already learned that some of these inductances are functions of theta. And this is because theta, the position of the rotor, is time dependent. We can easily solve this problem thanks to a powerful transformation. Now let's go back to where we stopped. This is a powerful transformation that eliminates the time dependency of inductances. We define three fictitious currents called ID, IQ and I0 on the left side of the equation in terms of actual stator currents IA, IB and IC on the right hand side of the equation. And its inverse transformation is given by this next equation. Here we transformed actual currents to fictitious currents. In the same manner, we can apply this transformation to define fictitious fluxes psi D, psi Q and psi 0, and also fictitious voltages ED, EQ and E0. Now I am going to leave 4 exercises for the students. In the first exercise, derive equations for fictitious stator fluxes psi D and psi Q. Equations 8 and 9. In the second exercise, derive equations for field fluxes psi FD and psi KD on the D axis and also psi KQ on the Q axis. In the third exercise, derive equations for fictitious voltages ED and EQ. And finally, derive an expression for power and torque in terms of fictitious fluxes and currents as shown in this slide. Now let's take a look at our new flux equations. So let me go back to that slide. The flux in the d-axis, psi d, depends on the d-axis current, id, and the currents in the other windings on the d-axis, IFD, IKD. The inductances in this equation are constants, unlike our original inductances in the flux equations. We also note that q-axis coils do not contribute to the d-axis flux. Similarly, q-axis inductances are constants and the q-axis flux does not depend on the d-axis currents. We make the same observations about the field fluxes. Psi FD depends on the currents in the d-axis coils. Same with psi KD, and psi KQ depends only on the currents in the q-axis coils. These equations suggest that we have two sets of coils, one on the d-axis and the other on the q-axis. Now if we look at the voltage equations, the voltage across fictitious winding D, ED, consists of three terms. Two of the terms are familiar rate of change of flux term and the resistive drop term. The other term in the middle, proportional to the speed of the rotor. That's the voltage induced due to the rotation. The rotational term in the d-axis voltage is proportional to the q-axis flux, and the rotational term in the q-axis voltage is proportional to the d-axis flux. The positive and negative signs are due to the choice of positive direction of rotation. In our case, it's anticlockwise. Now, the transform flux equations can be summarized in this diagram. Students should review those flux equations along with this diagram to get a good understanding of this transform system of coils. Now we can make our equations even simpler by introducing a per unit system. I am not going to discuss the per unit system here. Students should refer to the textbook by Prabhakandu and go through the numerical examples given in that textbook to understand the per unit system. So I am going to skip this slide and go straight to the resulting equations. Here we have the per unit voltage equations, and in this slide you see the per unit flux equations. And finally the per unit torque equations. Now let's focus our attention to steady state analysis. We know that at steady state the rate of change of any variable is equal to 0. Therefore, at steady state voltage equations do not have rate of change of flux terms. So the d-axis flux can be expressed as in equation 26. Also at steady state there are no currents in the amortisseurs. So the steady state flux equations simplify to equations 27, 28 and 29. Now with some substitutions and rearrangements of the equations, we can express IFD in terms of EQ, IQ and ID. The D and Q quantities in equation 31 can be determined if we know the position of the D and Q axis. In the next few slides, we will figure out how to determine the position of the D and Q axis and hence D and Q axis currents and voltages. Under steady state conditions, the phase voltages EA, EB and EC are balanced. Then by transforming these phase voltages to D and Q voltages, we get the equations at the bottom of this slide, ED, EQ. Note that theta is the position of the rotor with respect to the axis of phase A at time t. So theta is equal to its initial value theta naught plus the angle of rotation over the time period of t, or theta is equal to omega rt plus theta naught. Also at steady state the speed of rotor is same as the synchronous speed omega s. Now if we substitute theta in the equations for ED and EQ, we get these equations for ED and EQ. Since we use per unit, we can also write ED and EQ as ED equal to ET cos alpha minus theta naught and EQ equals ET sin alpha minus theta naught. Now consider the terminal voltage phasor ET. The last two equations in the previous slide, equations 32 and 33, suggest that ED and EQ are the projections of ET on two directions that are perpendicular to each other. Let us call these directions the direct axis and quadrature axis of synchronous machines respectively. The angle between ET and the direct axis is alpha minus theta naught. The angle between the quadrature axis and ET, 90 minus alpha plus theta naught, is denoted by angle delta. Also note that the direct and quadrature axes are defined in terms of theta naught. Therefore, they are measures of the relative position of the rotor. Also, ID and IQ are given by ID equals IT sin delta plus phi and IQ equals IT cos delta plus phi. Phi is the power factor angle. Now let the unit phasors along the direct and quadrature axis be D and Q in boldface. Then we may write the phasors ET and IT as ET equal to ED, which is the magnitude, times boldface D giving the direction, plus EQ times unit phasor in Q direction Q. And IT equals ID times D plus IQ times Q. We can manipulate previously derived equations 23, 24, 27 and 28 to show that ED and EQ can be expressed as equations 34 and 35. Students should do this as an exercise. Now let us define a phasor EQ. This is a new quantity we are defining. So we define EQ as ET plus RA plus JXQ times IT. We will see the significance of this phasor at the end of this derivation. We can expand the phasor ET and phasors ET and IT in terms of D and Q components. And now the component of EQ in the direction of D axis, the first term on the right hand side of the last equation, is equal to ED plus RAID minus XQ IQ, and the component of EQ in the direction of Q axis, that's the last term on the right hand side of the last equation at the bottom, it's equal to EQ plus RAIQ plus XQ ID. From equation 34, we know that ED plus RAID minus XQIQ is equal to 0. Therefore, we can conclude that the phasor EQ is along the Q axis. This is a very important result because we can compute EQ if we know the terminal voltage and current at steady state. When we know EQ, we know the direction of Q axis, and hence we can resolve ET and IT into D and Q axis to determine the components ED, EQ, ID and IQ. This is summarized in this Phasor diagram. So that's the steady state analysis. Let's now focus our attention to transient analysis of a simplified model. Now we are going to look at what's known as the third order model. This model has three differential equations. Two of these equations come from Rotor Dynamics. I will come to that later. The third differential equation is for the flux in the field winding. This third order model is commonly known as Efron-Phillips model. We ignore the damp windings. Then the equations for fluxes in the three remaining windings simplify to these equations. Now from the equation for the voltage of the field winding, we can get this equation 42 and 43 for the rate of change of phi FD, or the rate of change of flux in the field winding. We define three voltages. EI is a voltage proportional to the field current IFD. EQ prime is a voltage proportional to the flux in the field winding. And EFD is a voltage proportional to the voltage applied to the field winding, EFD. Now we can manipulate these equations to derive a differential equation for EQ prime. From equation 41, we get IFD as shown in the equation at the bottom of the slide. And we can substitute that IFD into equation 44. And also introducing the newly defined voltage term EFD. And also by substituting for LAD squared over LFFD in terms of XD and XD prime, the difference between XD and XD prime, we finally get equation 45, which is a differential equation for EQ prime, or it's the differential equation for the flux in the field winding. Now that we have derived the differential equation for the flux in the field winding, the next thing we need is the relationship between terminal voltages and current in terms of the variables of the machine. Let's take the position of the Q axis be at an angle delta measured in anti-clockwise direction from R axis, the real axis. Now it's important to note that the machines are connected to a power system network in a multi-machine power system, and the R axis or the real axis is the common reference for all the voltages and currents in the network. We have to express our D and Q voltages and currents into this common RI frame of reference, real and imaginary frame of reference. We can easily show that D and Q components are related to R and I components through these equations 47 to 50. I am going to leave this as another exercise for the students. Now we can express these equations in matrix form. Now let's look at the voltage terms EQ and ED. When we are interested in rotor angle stability, we are interested in low frequency oscillations. Typically these oscillations are below 5 Hz. Therefore we ignore fast transients and assume that any fast transients are highly damped and they disappear quickly. The fast transients are ignored by removing the rate of change of stator flux terms from the ED and EQ voltage equations. Then after some mathematical manipulations, we can obtain the relationship between DQ voltages, DQ currents and the field flux. As in equations 57 and 58, and then transforming this into real and imaginary frame of reference, we obtain equation 59. The elements of YG matrix in the equation 61 at the bottom of the slide are given by equation 62 to 65. Students should verify these equations independently. The two remaining differential equations come from rotor dynamics. The rotor dynamics is covered in any undergraduate power system course, so I am not going to go through this section. Students should go through the content of the next few slides to review the material. So let me skip those slides. So the rotor dynamics are represented by two differential equations. One equation for the derivative of speed and the other equation for the derivative of rotor angle delta. Now we have altogether three differential equations describing the dynamics of the synchronous machine. The first two equations represent rotor dynamics, and the last equation represents the dynamics of the field winding or dynamics of the field flux.